This is a nice application of the electromagnetic spectrum. What you're looking at is the radiation coming from you. If I turn out the light, for example, because you're all very warm, you will radiate infrared radiation corresponding to your temperature. We'll get into this actually. Hello there. Who's that with the hot hands? Not to be outdone. Okay. Hello there. All right. Okay. So we'll get into what is actually happening with this thing. Actually, to explain this was actually the origins of quantum theory, which we'll get to in a couple of weeks. But the fact that warm bodies radiate electromagnetic radiation is really quite an amazing thing. And it took Planck in the year 1900 roughly to understand it and to explain it as best he could. And from there became quantum theory. So this is, you're looking at really a very important phenomenon right now. And of course, this is the same phenomenon that is bringing energy from the sun. The sun is obviously a lot warmer than we are, and it radiates a tremendous amount of visible radiation. You are radiating what's called infrared. Infra meaning below, like an infrastructure, below the substructure, sub-red radiation. And this camera is able to see that, just as your eyes can see visible light, this camera is able to see this infrared light, and it's making a color scale on the right side, you see, corresponding to the temperatures it's seeing, because the frequency of the radiation you're sending out depends on your temperature. And so different parts of you, like my hands here, my fingers, but my pinky, let's see, this one, pretty cold. And we tested this before. I tend to have a cold nose. Is that true? I can't, yeah, kind of bluish, I'm sorry. So, does that make me a warm heart? No, no. There's some kind of superstition like that. In any case, you'll be able to come up and test yourselves later on that. So we'll go over to some theoretical things. I hope. Here we go. Oh, not right now. No, sorry, I don't want that. I wanted to pick up where we left off. Well, running through this very quickly, the idea was that Maxwell put together the laws of electricity and magnetism as he knew them in 1860, learning from Ampere about magnetic currents, learning about Coulomb from point charges. Gauss's law he knew, but he added the way magnetism is created by currents, but he added one particular thing which was very important, namely that in addition to ordinary currents producing magnetic fields, which is this Ampere's law, which we saw before, in order to satisfy a number of criteria, important things, he said, let's take into account the fact that even in empty space, if you have a time-varying electric field, a time-varying electric flux like this, it acts as though it were an electric current, and just the same way as a real current flowing in a wire produces a magnetic field. So he put that out as an idea, and as a consequence of that idea, that there is this so-called displacement current due to the flux of the electric field. The flux being the usual thing we've had before. We actually had the E dot dA before, which we call the electric flux. That was Gauss's law. So you could write that as d flux electric. We had a Gauss's law integrated over a surface, again over a whole surface. If you integrate that, you get Gauss's law, right? Q over epsilon naught. So we know what the idea of a flux is. Usually it's a field times an area. So it sort of captures the amount of lines going through an area. We also have the magnetic flux, which is B times an area, a dA. Okay, so, but what Maxwell added was the idea that this actually acts like a current. A changing electric flux in time will act like a current, which he called the displacement current. And so if you have that, you will get some magnetic field around it. So you add that to the Ampere, and you get the so-called Ampere-Maxwell equation. The first term on the right is what Ampere said. The second term is this mu0 times this displacement current. And this completes the equations we have for describing the sources of electric and magnetic fields. All electric and magnetic fields that we know about can be explained and understood on the basis of the four equations that Maxwell assembled and added to. So you have the electric fields created by charges and time-varying B fields. That would be Faraday's law. And B fields are created by moving electric charges, that's just a current, would be Ampere, and also time-varying electric fluxes, which would be Maxwell's induction. So that creates the fields. And then if you put other charges or currents in those fields, you get forces acting between them, or among them if there are many. And one of them is the sort of Coulomb force, F equals Q that you put in times the field, or the Lorentz force. You could have QV substituted by IL, I and L, I being the current, a moving charge, and L being the length. So that would be the Lorentz force, or sometimes it might be called the Ampere force. Right? So we're familiar with that. So this is the whole story, actually, and we built up to this. This is really a big climactic point in the course, and it's a climactic point in the history of science, because we understood where all these electromagnetic forces come from, and it turns out that it's basic to understanding our existence, because it's electric and magnetic forces that hold atoms together, make solids, and makes us what we are. So here they are again collected. Now this is for the case in which there are no material charges or currents present. In other words, there's no Q. Well, it looks like there is a Q over here. Let me see if I do, in the absence of charges and currents, then my Gauss law would say there's no charge there. So this is empty space. No charges, no currents. Well, this one is because there are no magnetic monopoles at zero always. In the absence of, okay, Faraday always works. There's a changing B flux, produces an electric field. And here we have the Maxwell part, which is left if we have no steady currents. So that, well, that's what happens in the absence of material charges, so in empty space, which is very important because from this we're able to derive an equation. Maxwell was able to derive an equation which looks like a wave. And we talked a little bit about the properties of waves. I'll mention it again quickly in passing. And what I wanted you to appreciate was that we're going to go over a number of different kinds of waves in the remainder of the course. The most important are the two most important, electromagnetic and also quantum waves. It's going to turn out that material things have a wave property. Matter does. This is the Schrödinger wave equation, or de Broglie's idea of that matter has wave-like characteristics. And I want to have an idea of the general properties of waves, because you'll be applying it at times to, say, ultrasound, the wave, sound is a wave, and they'll all have these properties, and so you shouldn't be surprised when you come across them. For example, we have the wave has a speed, namely how fast the crests move across space. It has what's called frequency, wavelength, and amplitude. And there's a Doppler effect, which the frequency will depend on the relative motion of the source of the sound and the observer of the sound. The Doppler effect is familiar to apparently to all of you. The waves will have polarization, they'll carry energy, they'll carry momentum, they'll exert pressure, they reflect off things. As I pointed out, we mostly live in reflected light. They refract if they bounce off a medium, like they're bouncing off me, and that's why you see me, and I see you, because the light's bouncing off you. Also, if the light penetrates into the medium, it will... Here's the interesting thing. In order to get reflection and refraction, you have to get a different wave speed, because the velocity of the wave is equal to c in a vacuum. This is a very obvious point, but you do want to have it sharply in your mind. In a vacuum, the velocity is c for all light waves, EM. I shouldn't say light waves, all electromagnetic waves, regardless of the frequency. Regardless of the frequency, or corresponding to wavelength, or the amplitude. But not every wave does that. Some waves, depending on the amplitude, they will change their speed. For example, water waves, I'm not quite sure actually how they are, but when a water wave approaches a beach, it sort of peaks up. You know how it changes its shape? See, a light wave won't do that. Well, you'll get reflection off a surface, but water waves and other kinds of waves will have dependencies on frequency, wavelength, and amplitude. But light waves in a vacuum, electromagnetic waves, very carefully, electromagnetic waves, meaning that they are a combination of an electric and magnetic field traveling through space, E and B. Now, again, the direction of E cross B, in this case, is in this direction, so they'll be traveling with a velocity in that direction. And all of them, regardless of the frequency, whether it be this infrared light coming from you, or the visible light, or a radio wave, or an X-ray coming from an exploding star, or a gamma ray from a nucleus, they all travel with the speed of light, independent of their frequency or their amplitude, through empty space. But in a real material, it's different. And that's, if you go from a vacuum, or air is pretty much a vacuum, actually, to a medium, we describe that medium as far as light is concerned by what's called the index of refraction, which is a function of frequency, well, and in turn wavelength. And in fact, well, you might even get amplitude effects, but we won't worry about that too much. The point is that in a medium, the velocity typically slows down. N is greater than 1, typically. And it means the velocity slows down. And the point being that whenever light, or any wave, travels from one medium where its velocity changes, you'll get two effects. One is reflection, because it senses there's something different. So that you've lost your symmetry. You're going along in a medium, your velocity is constant, and if you hit something that has a different wave speed, you'll always get some reflection, if the index is different. And possibly you'll get the light, or the wave, speaking very generally, possibly will enter the medium. Sometimes it's totally absorbed right at the surface, so it doesn't travel through. For example, light does not travel through this paper. When I put this up, you don't see me anymore. So the light has come here, and it's totally absorbed in the paper. On the other hand, there might be some medium that's semi-transparent. This one might be one. Let's see. Yeah. So you see, this is semi-transparent. The light from me is passing through, and you can roughly, I can see you guys. You can see me too. Okay. So it's semi-transparent. It's darker. So some light from me is being absorbed in the medium. The rest is getting through to you. And so there are various possibilities. But in any case, if the light is able to get through, it will bend. If it comes in at an angle because of the different speed, it will refract. In other words, light coming in at some angle, see, it's going to bend closer to the thing. So it comes in this way. It will bend toward the normal. I think you already had a lab that may involve this, and we'll get into it in great detail later on when we talk about optics, because this is now optics. So those are some general properties of all waves will do this. Namely, if there's a different medium, some of it will reflect, some of it may go through, and if it goes through with a different velocity, it will bend, refract. It may be absorbed in that medium. Some mediums are totally opaque, and some are totally transparent, like glass windows, are very transparent. Or they may be semi-transparent, like that Polaroid sheet that I picked up. Now, again, so that's general. And also waves will tend to bend around obstacles, which we'll get to, and they can interfere with each other, and they can form standing waves, all of which are very important properties, generally. So the beauty part is, anytime you hear about a wave, you can look on this list, and the wave will do all of those things. That's very handy. I remarked that when de Broglie said that matter is a wave, you could win Nobel Prizes if you just went ahead and measured the refraction of an electron passing from one medium to another. That would be a Nobel Prize experiment. In fact, diffraction won a Nobel Prize. Diffraction of electrons as a wave on a medium was a Nobel Prize-winning experiment. Interference of electrons, well, standing waves of electrons, certainly that's what Schrödinger said. He said that the electron going around an atom is a standing wave, because it's a wave. And that was the energy levels. So there you go. I think people do talk about polarization of electrons at this point too. Okay, so you do want to be very clear on the meaning of the terms describing a wave. The distance in space is called the wavelength. The time between similar points in time is called a period of time. Now, you don't want to confuse it with the amplitude, either of those with the amplitude, because the amplitude is how much displacement there is of, or magnitude of the stuff that's going. In other words, this could be the electric field. A here could be an electric field. So it's the magnitude of the electric field, or it could be the magnitude of a voltage, or it could be the magnitude of a magnetic field. It's not a length, it's the stuff that's moving. It could be the gallons of water in a wave, would be the amplitude of the wave. In the case of a water wave, you might say, well, it's a 10-foot wave. So, but that would be an amplitude. You're not talking then about the wavelength. The wavelength would be the length between two crests of waves coming in. Namely, how much time do you have to get up after the wave hits you? That's one thing. The other thing is how big the wave was. So if you go to a place like Mavericks in Half Moon Bay, they have 30, 40-foot waves. They're talking about the amplitude. They're not talking about the length. Because if the length is 30 feet, but the wave is this high, they're bored, right? So amplitude is one thing. Wavelength is something else. Got to make sure, because that's very confusing. I've said that before. Okay, then we had the idea that the electromagnetic wave, this particular kind of wave, it has the properties of having both E and M, and they're perpendicular to each other. And because of the mechanism of how they generated, that is to say that the changing magnetic field produces an electric field, and the changing electric field produces a magnetic field, you would think that the two amplitudes should be related to each other, because one is creating the other. And in fact, the ratio is of amplitudes to each other. This is an important fact, that E over B in an electromagnetic wave was always equal to C, amazingly enough. And that is plausible, because the electric field is creating the B, and the B is creating the E, so you would think as much as B is just that much, there's going to be a ratio of B to E, and it turns out to be C in a vacuum. So that's a good point. Then I displayed Maxwell's equations, which are a little bit explained in the book, and I'm not going to go through the derivation. It's not too bad, but it's tedious. And but the amazing thing that came out was that the final result that you do get a wave-like equation, namely something which is a field of amplitude b, which is varying in space. Here's your dx squared, is related to that same field varying in time, and it's related by this quantity here, which is actually in the inverse of the square of the speed of this wave. If you harken back to the general wave equation, there was a parameter in front of this thing here, which was a v squared. So it turns out that v is equal to epsilon naught mu naught inversely the square root, and that's from electrostatics. We knew what those numbers were, and Maxwell plugged them in and found that he got the speed of light at the minute. And you'll notice that in this speed, the frequency does not appear, the wavelength does not appear, and the amplitude does not appear, meaning that any wave containing an E and a B will have this speed in vacuum. So that's kind of the proof. If the wave equation turned out and that V had frequencies or wavelengths in it, then you would have a very different thing. Then maybe a high-frequency wave would go slower, or maybe a low-frequency wave would go faster or something, but that's not the case here. And I recall to you that they all go with the speed c. Yeah, and they have this ratio. And of course, the very important relation is the velocity is equal to the frequency times the wavelength. That's a fundamental fact. The frequency is in units, number of cycles per second, and the length is in meters. So this is meters per second, so that at least has the correct units of speed. And that's what we have. So continuing with this, the famous Maxwell T-shirt. And so again, in vacuum, for all the frequencies, you have the velocity c. But in materials, you don't, and that's the interesting thing. This gives rise, in fact, in materials. If you can measure the velocities of the light in materials, the reason the velocity is changing is because the light is interacting with the atoms. It's shaking the electrons. And if you're in sort of resonance with the electrons, sort of like that demo of the moving spring, if you can get into step with that, you get big motions and you get big reactions from the material. So by sending light into a material and shaking the atoms, if you get near a resonance of an atom, you get a big response. And so you can study the interior properties of materials by shining different frequencies of light in there. That's known as spectroscopy. Spectroscopy, you send in different spectra into a material, and you see how it reflects or absorbs, and you can then try to go back and figure out what's in the material that's changing that. And that's one of the best ways of understanding how materials work, is by shining light on them and seeing how the material responds. And that's a frequency and wavelength dependent response. So we do spectroscopy in the visible, we do spectroscopy in ultraviolet, X-ray spectroscopy, big business. And you've probably done infrared spectroscopy to learn about the vibrations of molecules, right? You get absorptions. Do you do IR spectra in chemistry? Yeah. Well, what you're doing is you're shining in light, and you're asking, do I see a resonance? Do I see the light being strongly absorbed or strongly reflected? And that's telling me, oh, there's an OH bond, or something like that, if I see that peak. So that's what you're doing. And so that depends on the fact that the light wavelength or frequency is in tune with some resonance, and it's changing the speed or the absorption near the resonance of the material. So that's familiar to you, actually, I would think. Okay, so then we have the idea of that ratio being a constant equal to the speed, which is plausible. I can't prove it to you without a lot of math, but it's very plausible since they're creating each other. And that they're perpendicular is not particularly obvious, but it turns out that they are, and they are transverse to the direction of propagation, and the direction of propagation is given by this cross product. Somebody was trying to figure out how you do that. You point your fingers in the direction of E, turn it in the direction of B, and the thumb will point in the direction of which way the wave will go, and you can know that. And then we went over these various spectra of radiations. They come in all frequencies from very low to unimaginably high frequencies, like 10 to the 15, 16, 17, 10 to the 8.